Assalamualaikum warahmatullahi wabarakatuh. Today our group will present about stretchable conductive ink, background study. Flexible and elastic electronics are made using a substance called stretchable conductive ink. Because they are flexible and easily bendable, these electronics and advantages for wearable technology. Numerous useful use of wearable technology exist in the field of healthcare, energy, and the military. The industry for wearable technology is expanding as a result of development of SCI and flexible electronics. Next, we will talk about the problem statement. Okay, for the problem statement, the demand for printed circuit boards (PCB) now exceeds supply, which result in high cost and labor-intensive process due to problem with the supply chain for conflict minerals. By choosing a replacement material for the flexible PCB board that is highly conductive, elastic, and dependable under different strain and temperature conditions. Okay.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zain Nasir Biraimi, and today I will explain the application of nanocomposite. First, bond tissue engineering application. Nanocomposites are excellent at replicating the organic shape of the extracellular matrix that surround cells, which are ideal for promoting tissue repair. This extracellular matrix has three main characteristics. First, combination of macro-sized molecules. Second, fiber structures that have length to diameter ratios higher than 100. And lastly, smaller than 500 nanometer in diameter. Nanocomposite helps the formation and growth of bones due to the fact that scaffold with surfacing glycines, similar to natural bond, will aid in the growth of novel bond at the cell or biomaterial surface. Sensor application. Nanocomposites are frequently employed as suitable materials in a variety of sensor technologies due to their customizable porosity, excellent thermal and chemical durability, high selectivity, and simplicity of construction. Nanocomposites that usually used are chitin that has been modified with metal oxide compounds because of some of its properties. For instance, ease of field motion, high mechanical strength, biocompatibility, high water permeability, and susceptibility to chemical modification. Lastly, optical application. Nanocomposite that made from two or more different materials with varying mechanical, electrical, and chemical properties are offered a novel way to enhance the workability and stability of materials with unique optical features. Biorenewable materials such as cellulose have been used in the synthesis of many types of nanocomposite structures as the major component of material. Nanocrystalline cellulose dissolved into a polyurethane matrix increase the mechanical property of the cellulose polyurethane structure. Despite having 84% optical transmittance, the nanocomposite prepared with cellulose dissolved in polylactic acids have very high mechanical properties.
Assalamualaikum warahmatullahi wabarakatuh. So today I will continue presenting about the material development. 3,4-ethylene diacetylene or E-dot can be converted into P-dot chemically or electrochemically. The polymerization of polystyrene sulfonate (PSS) and aqueous polyelectrolytes results in a water dispersible product that is stable, simple to produce, and has good film forming capabilities. The conductivity of P-dot PSS films made from aqueous dispersion is less than that of P-dot films made using oxidative and vapor phase polymerization and stabilized with small molecular ions. Multi-wall carbon nanotube or MWCNT. The game-scale growth and purification of MWCNTs using an enhanced arch discharge technique. For the creation of carbon nanofiber or MWCNTs, Endo and other writers create a following catalyst reactor in the 1980s using catalyst particle of a 10 nanometer diameter. It is proper to call the carbon fibers MWCNTs. The synthesis of CNTs is active in transition metals, particularly in ferrum, copper, and nickel. The majority of the time, co-precipitation or other loading techniques that are used in chemical and petroleum process are employed to load these active components onto a catalyst support. But because the CNTs are deposited on the catalyst surface rather than going on them, the catalyst is not actually a catalyst because it is only utilized once. A single wall carbon nanotube or SWCNT. Due to the insanely high energy input, the arc discharge and laser ablation procedures may produce SWCNTs with high quality and few flaws. CVD is helpful for scaling up SWCNT manufacture since it can be carried out at a low temperature, a bit greater than the utilized for SWCNTs. The most extensive research catalyst for the industrial manufacture of SWCNTs is made of ferrometal nanoparticles. The primary challenge in the manufacturing process is to keep the metal nanoparticle dispersed. Diameter is lower than 3 nanometer during CVD growth. Thermoscientific Polylab or SOE mix or thermoelectrocompression in the USA was used to create polymer nanocomposite based on TPU utilizing the intercalation process at 185 degrees Celsius, 100 rpm and 6 minutes mixing time. For the purpose of evaporating any moisture present in the given materials before combining, nanoclay and TPU were dried in a vacuum oven at 80 degrees Celsius and 12 hours. By compression molding TPU and its nanocomposite sheets at 180 degrees Celsius, samples for mechanical testing were punched from the mold sheet in accordance with the standards. Where X stands for 1, 3, 5, 7 and 9 weight percent of organoclay injected into a 100 weight percent TPU matrix. P stands for organoclay made of chloricid 30B. That's all for me. Thank you.
So next is the formulation of stretchable conductive ink materials. For the matrix material, we chose the poly-3,4-ethylene dioxythiophene polystyrene sulfonate, or as known as P.PBS. P.PBS is the most common example of an organic conductor. It is highly flexible, largely transmissive to light, processable in water and highly conductive. P.PBS is an advanced from P. material that create a polyelectrolyte complex consists of positively charged and P. and negatively charged and water soluble. Despite having very good electrical conductivity, excellent transparency and thermoelectric properties, as well as low sheet resistance, P.PBS still have numerous things to be developed before it can be applied in industry. For the metallic fillers, we choose carbon-based nanomaterials, CNT, and CNT have been observed to hold immense potential for use in both printed and flexible electronics. Moreover, CNTs also have created high interest compared to other nanomaterials because they are electrically heterogeneous. However, the suspension of CNT in water is still not stable, and it remains a subject of concern as the nanoparticles often appear to form in clumps quickly due to their strong van der Waals extraction as well as the occurrence of toxicological problems. CNT also have an extremely high aspect ratio exceeding 10 to the power of 6, a Young modulus of 1 terapascal, a tensile strength of 100 gigapascal, and a current carrying capacity of 109 ampere per centimeter cube. These superior properties make CNTs fascinating nanomaterial for stretchable conductor. And lastly, for the substrate material, we choose the thermoplastic polyurethane TPU, where TPU is an exceptional material for the flexible electronic sector, with a typical elongation in the vicinity of 700%, TPU is ideally suited for flexible electronic due to its high flexibility, even at extremely low temperatures, and outstanding tear and abrasion resistance. TPU, which resembles rubber and feels smooth to the touch, is sometimes referred to as the bridge between rubber and plastic. The film is also renowned for its breathability, which allows the manufacturer to customize the amount of moisture transferred through the film by using different polymers and additives. The film is frequently offered as a 3-layer sandwich of a matte adhesive layer and a temperature-resistant carrier.
Okay, 5.0 material characterization. We have done 3 tests, which is 5.1 mechanical test, 5.2 thermal, and the last one is electrical test. Okay, now let's move to the mechanical test. Mechanical test that we do is cyclic stretch strain test. Okay, the procedure is the experiment was set up by attaching the stretchable printed circuit to both bodies using 2 holders. The holder detach from the body, making it easier to attach the circuit. Figure 1 show the setup of the circuit for the testing. During the testing, both holder will clamp both sides of the circuit. When the spindle is turned, the main body will push the secondary body, causing the printed circuit to stretch. Okay, the last one, the lock mechanism will allow the test ring to hold the position when needed. Okay, as we can see the picture or the suitable diagram, we have the setup of the stretchable printed circuit for strain testing. Okay, now let's move. Okay, here are these 2 samples to obtain the bulk resistivity. The first one, we are using the V is equal to IR, and the second one, we use resistivity by using 4-point probe test. Okay, the formula is RS is equal to G times V over I. Okay, now let's move. Okay, now the thermal test, we do the 3 in situ experiment. Okay, the testing procedure. The first one, for the thermal test, the conductive ink sample was heated to low temperature, which is the 40 degree, intermediate 60 degree, and the high is 80 degree for 30 seconds before the sheet resistance was measured using the 4-point probe. Okay, next, the room temperature is used as reference point during testing. Thermal imaging analysis was used to determine the heating level in situ. The thermal figure will show later. Okay, now let's move to strain test. First one, the sample was stretched at different level in room temperature. The sample stretched under room temperature at strain level of 0%, 20%, 40%, 60%, and the last one is 80% of strain. The initial length of the sample is 20 mm, and the sample was stretched until a maximum of 36 mm. The sample was set to stabilize for 30 seconds before the resistance was measured at each strain level. For strain test, the figure the figure 2b was shown there. Okay, now let's move to next slide. Okay, for thermal strain test, the procedure is the sample was stretched to a various strain level, which is the 0, 20%, 40%, 60%, and 80%, followed by the concurrent heating at the room temperature. Okay, the 40 degree, 60 degree, and 100 degree for 30 seconds before deploying the 4-point probe Okay, the first one is the thermal, the second one is about the strain test, and the last one is about the thermostrain test. Okay, the theoretical formulation: P.PSS was filtered and measured and mixed thoroughly for 2 hours using a 0.2 meter sharing to make a composite binder. 10% polyacrylic acid PAA added to P.PSS, which sonicated at an hour to achieve homogeneous dispersion of P.PSS and PAA. The TPU substrate 15 cm by 4 cm were accurately cut and used to create freestanding electrode film. P.PSS thin film cotton with TPU substrate were homogeneous and bendable. Printed film were dried for 12 hours in an air oven before being annealed at 120 degrees Celsius to reduce moisture. Okay, 5.3, the electrical test. Okay, the first one, we do the resistivity measurement, which is the stretching with a certain elongation values. Resistivity measured using a 4-point probe, as shown below, as shown later. Okay, they investigate resistivity of the for conductive ink under the tensile stress. Also, effect of elongation on resistivity performance. Hence, the longer the length of conductive ink, the better the conductivity of the conductive ink. Okay, the procedure is at the initial length, the conductive particle inside the conductive ink are having a full contact. Hence, the resistance is low at 500 ohm per square for 40 mm, 60 mm, and 80 mm. However, during the stretching process, distance between the conductive particle increase gradually with a percentage of elongation. The increase of distance between the particle causes an increment in resistance because the contact area is reduced. Elongation of conductive ink has significant resistivity, where increase of percentage elongation causes the higher resistance. Okay, this shown how the test was set up. Okay, the first one you can see what we call is the resistance of 40, 60 and 80 mm length that measured by 4-point probe. We can see the result, resistance per square over the elongation, percentage of elongation. Okay, now in figure 4 we can see clearly what is the 4-point probe. Okay, the theoretical formulation is the carbon conductive was printed on the TPU and cured in the oven at 120 degrees for 30 minutes. The resistivity was measured by a multimeter, and the shear resistance was measured by a 4-point probe. At the initial length, the conductive particle inside the conductive ink are having full contact. Hence, resistance is low at 500 ohm per square for 40, 60 and 80 mm. However, during the stretching process, the distance between the conductive is increased gradually with the elongation percent. Okay, now 6.0 shown the conclusion. Okay, 6.1, recent advance in SCI technology. Surface quality of SCI deposited on the TPU substrate, defining SCI on electrical and mechanical properties, particularly for wearable and and electrical efficiency as well as product quality are greatly influenced by curing temperature. The mechanical and the thermal effect has been intensively investigated for its potential to improve metal filler conductivity. SCI has great capabilities, large demand, and demonstrated tremendous potential in wearable healthcare, advanced diagnostics, soft robotics, and persistent human-machine interfaces. SCI nerve as interconnect key enable for stretch electronic. SCI also push traditional design to new height by create attention, surprise with interaction with the environment. Okay, now let's move to 6.2, which is the challenges and opportunities of the SCI in the future. Okay, the challenge of SCI is part of its applicability limited by a reliance on low throughput, high cost fabrication method. However, many good reasons to implement SCI as combination. Example, combination driver monitoring system and SCI sensor layout to prevent road accident caused by driver behavior and improve the driving monitoring system with soft substrates technology that give advantages on geometric deformation based on appropriate shape. The benefit of advanced SCI technology used to mimic the function of the human skin, and it can be strengthened by converting human skin stimulation such as pressure, temperature, tension, humidity, and a variety of the factor into the electrical impulse. Human body can interfere flexible, conductive ink, and compatible with human supple and sensitive nerve. RFID tag is one of the application of conductive ink. For example, it used to automatically identify clothing product. The stability and the flexibility of the printed carbon nanotube sheet are good. According to a study, a carbon nanotube conductive ink optimization employing solvent exchange technique for flexible electronics application. As a result, printed film is good things of flexible electronic application. Finally, the challenges development of is achieving great mechanical and electrical performance at the same time. It is a must to maintain the mechanical and electrical performance under extreme strain. Overall, the SCI technology is not replacement for microelectronic manufacturing, but it is an opportunity to produce large area of flexible electronic devices at low cost. That's all for us. Thank you, madam. Sorry if we have something that not good in our presentation. We apologize and hope we can improve in the future. Thank you, madam. Assalamualaikum.
For the summary of our presentation, stretchable conductive ink is a useful substance that after stretching and folding improve the electrical and conductivity of the ink film. Nanomaterial is based on carbon teflon, huge potential for usage printed and flexible electronics. Through interaction with the environment, this technology will elevate conventional design to new